Greeting, oceanographers. This is Mr. D, and this is your first set of notes for our first sort of little unit. These notes will be in two parts, so this is the first part of two parts of notes. And what these notes are about is addressing our first essential question of the course, and that is, how is the ocean the defining feature of the Earth? And we're going to be tackling this question for a number of weeks, but to begin tackling it, we want to consider the geologic features of the ocean. And what that means really is that if we sort of think of it like here is a very detailed diagram of the ocean. Here are the waves, okay? All of the water and the life and the processes that go in there is so much of what we'll be exploring this year in oceanography. But the first thing we want to talk about are the geologic features, which are really kind of the rocks, the hard part that makes up the ocean basin. All of the stuff that's under here, the basin of it. The ocean basins, they're composed of the sea floor and all its geologic features. These features vary in shape and size due to the movement of the Earth's crust, which is known as the lithosphere. Now, a quick sort of story on this. If we look down here, I mean, this is what, here's sort of a map of North, South America, Africa, and Europe. And only until about 60 years ago, this is what we knew. We knew what was on land. We knew it was over here. We could go across in boats. We could go across in planes. But all of this other part of the Earth, we had no idea. And it wasn't until, really, World War II. In World War II, a little confrontation between Europe, Germany, United States. Over here, submarines were going back and forth during World War II. And actually, if we think of the submarines over here, as they were going back and forth, they used a new technology called sonar. Sonar is sound navigation and ranging. And they were able to look out for mines, but they were also able to look at the ocean floor. And every time the submarines went across the Atlantic from Europe, either over to North America, or North America back to Europe, they always noticed there was sort of a ridge that they'd come across the bottom. No matter where they crossed over here, they went over this little ridge. And so after World War II, they thought, well, maybe if we could use this sonar to get a better understanding of the ocean floor, let's see what's down there. And so in the 50s and 60s, sonar was used to sort of map the ocean floor and discovered a whole bunch of stuff. There's a lot going on the ocean floor. In fact, if I take away the water, this is all the stuff that's going on here. And just as sort of a quick point, we do have, sure enough, this ridge that runs down the middle of the Atlantic. We have things called fracture zones. We have these little bumpy seamounts that are all over the place. We have places that are super flat, I mean flatter than flat, called abyssal plains. We have things called trenches. There's so much going on down there, and that's sort of the first part of what we're thinking about here. Okay? So, how did these features come to be? They have to do with the movement of the Earth's crust. Now, the Earth has sort of this outer crusty layer called the lithosphere, and that crust is broken into plates. This is what we know now, that our crust, our outer crust of the Earth, is broken into plates. And on Earth, there are 7 major plates with some minor plates, and these plates are constantly moving around, and they're constantly being recycled. So if you can see here, here's the Pacific plate. It's sort of moving in a general northwest direction. Here's the North American plate, here's the Eurasian plate, African plate, South American plate. These plates are splitting apart from each other. It's interesting to note, too, where we are. If we're at the edge of the plate or in the middle of the plate, you look where we are, even though we're near the edge of the ocean, we're still in the middle of the plate. So just because we're at the edge of the edge of a continent doesn't necessarily mean we're at the edge of the plate. We'll talk more about that in the second part of notes. Okay? So, and the best way I sort of think about the plates on Earth, imagine a swimming pool. Imagine a pool that has all these styrofoam pieces that are in the pool. And they're all kind of close to each other. They're filled with these styrofoam pieces. And sometimes the pieces can bump into each other. Sometimes one piece might push up on another. Sometimes pieces might come apart. And sometimes pieces might slide together. If you can picture these styrofoam pieces floating on a pool, it's kind of like the plates of the Earth. They're floating on the liquid magma that's underneath. If you click down here, you can watch a really cool video, an online video about how the plates move around. And please do that. You can do that now, come back to this video, or you can do it at a different time. Okay, so key idea. Our seafloor is spreading apart what we now know as these ocean ridges, these mid-ocean ridges. And where this occurs, there is new crust forming. As the plates split apart, magma comes up, cools, and creates new ocean crust. And then, as the plates move along, eventually this plate will be pushed underneath another plate. And where this plate is pushed underneath another plate, it's called a subduction zone. And where you have a subduction zone, you have trenches. And after this, when this rock that's created, this new crust is pushed down there, it melts. And this is the key thing, is that as it melts, it's recycled, and it's recycled into new rock. The rocks all on Earth are recycled. In fact, everything on Earth is recycled because Earth as a system is a closed system. The neat thing is that as you sort of look down here, it melts, and as the crust melts, it can kind of bubble up a little bit and cause volcanoes. When you have volcanoes, volcanic activity, new crust is forming. In fact, over here, same idea. It's going underneath, comes up, creates volcanoes. Now, if an ocean plate's going under a big continent, these volcanoes can create mountains. And an example of this is the northwestern part of the United States. This is like, you might have heard of a volcano in Oregon called Mount St. Helens. In 1980, Mount St. Helens had a very big explosion. This is similar to where the Juan de Fuca plate is being pushed under the North American plate, creating a ridge of volcanic mountains in the northwest. Or sometimes an ocean plate can go under another ocean plate. Sure enough, volcanoes are also occurring, but these now volcanoes sort of stick up in the ocean, called the volcanic arc. This is like Japan. Japan is an example of this, where the Pacific plate is actually being pushed underneath, believe it or not, the North American plate, creating volcanoes. One other neat thing to think about too is that as these plates are pushed underneath the one, right along here, you get lots of friction. And where there's friction, there's earthquakes. So whenever you have subduction zones and trenches, you have a lot of earthquakes. Sure enough, this is the situation that recently happened in Japan. An earthquake off the edge of Japan created earthquake damage and then tsunamis, which we'll talk about a little bit later on. Okay. Now, I was sort of getting ahead of ourselves. Ooh, wait. Quick side note. There's also a cool video here about seafloor spreading. You can watch that video now. Hit pause on this one, come back, or you can watch it at a later time. But please watch it. It's a good way to sort of see how these processes work. All right. Now, sort of getting ahead of myself here, because how do we know this? How do we know that the Earth is made of these plates, and how do we even know these plates are moving around? The truth is we didn't know the Earth was made of plates, and we didn't really think about them moving around until only recently. But before thinking about how the plates were there were scientists thinking about the fact that the continents were moving. Now we now know that the continents are kind of on the plates, and as the plates move, so do the continents. So what evidence is there that our continents are moving? And there's a number of pieces of evidence to do so. One such piece of evidence that supports that the continents are moving, or in some ways we can say drifting, is that sort of the puzzle piece. Think of it as the sort of puzzle piece of evidence. And that is, if you look at the continents today, North America, South America, you can see that perhaps they sort of fit together nicely as if they were part of a puzzle. So working backwards, if that was the case, if they are now drifting apart, if we go back in time, it must have meant that they were once together. And we now know that that is true. There used to be a supercontinent called Pangaea that was there before the time of the dinosaurs. And when Pangaea started to split apart about 200 million years ago, that's when the dinosaurs came to be. So it was about 200 million years ago that a supercontinent named Pangaea split apart. And those different plates started moving apart. But that sort of intuitive backwards thinking, that the puzzle shapes of the continents can fit this idea of moving continents. Another piece of evidence, or two other pieces of evidence here. One is that we can find similar rock types. If we look in the Caledonian Mountains up in Norway and Scotland, we look at the rocks, the mountains and the rocks of North America and the Appalachians, these rocks are very similar. So similar that they think they were formed at the same time in the same place. If they formed at the same time and at the same place, they must have been together before. And sure enough, we now think these rocks formed during some mountain building activity back when Pangaea was around. And since that time, the continents have split apart. Another piece of evidence, if you look down today along the southern tip of South America and the southern part of Africa, even the southern part of India and Australia, we find glacial deposits, as well as Antarctica. Glacial deposits, sort of quick side on that, glaciers. When you have a whole lot of snow, the Earth gets cold. You have a lot of snow, that snow turns into a lot of ice. When the Earth is in cooler stages, that ice becomes huge, creates huge ice sheets, and these ice sheets move across the continent. As they move along, they leave lots of debris or deposits. They leave boulders, rocks, they leave scrape marks in the ground underneath them. They kind of bulldoze sediment. They leave a lot of telltale signs that glaciers were around. Well, today we find these glacial deposits almost near the equator. That doesn't make sense. How could there be glacial deposits near the equator? In Africa and India, it's super hot there. How could there be big ice sheets? Well, wait a minute, maybe, thinking backwards, perhaps these continents weren't near the equator in years past. Maybe about 300 million years ago, they were closer to the South Pole. That again is sort of this backwards evidence to think perhaps these continents were closer together and since have sort of drifted apart. Last piece of evidence to think about this is the fact that we find similar fossils on continents now far apart. We find Mesosaurus fossils, which is sort of an underwater dinosaur, and we find them in South America and Africa. Now wait a minute, now a long time ago it wouldn't make sense that they could be found in this part of the country and this part of the continent and in the southern part of this continent. But perhaps when South America and Africa, if they were closer together, it would make sense that this is where the animal lived, and since that time, after those fossils were deposited, they split apart and create, and now that this is why we now find them so far away. So those are really just sort of the first general pieces of evidence to think about our continents are drifting. Now, that was before World War II, thinking of these evidences. Since then, since World War II, and I told you about the sonar, scientists have really been able to now study the ocean floor itself. And looking at the ocean floor, we can find more evidence that the seafloor is spreading at mid-ocean ridges. And this has to do with the fact that Earth's magnetic field doesn't always sort of stay the same. Right now, Earth's magnetic field is such that north, if you have a compass, north is pointing north, south is south. But north and south weren't always the same. And in fact, we now realize that in Earth's history, there are periods where the poles sort of switch, where south becomes north and north becomes south. It doesn't happen instantly, not in a day or not even in a couple hundred years, but usually in about, I don't know, 10,000 to maybe 100,000 years. For the life cycle of a planet, that's not that long. So how does this sort of help scientists think about this idea, sort of prove that the seafloor is spreading? Well, when scientists took samples of the current seafloor, and they looked down here, and they realized that, well, the samples that are near the middle of the ocean, the minerals that are in those rocks are aligned in a certain way, that north is north and south is south. But if they look at the rocks to the east and the west on the ocean floor, they're switched. In this case, the rocks are aligning themselves that north is actually pointing south and vice versa. And then they look further away, they see that again there's another band where it looks like the poles are pointing so much to where they are today. And that sort of thinking got them, well, let's sort of think backwards. Perhaps if these rocks were formed, call it sort of a time of normal magnetism, and where the poles were such that, say, South Pole was pointing there in the southward direction, those rocks formed and the minerals in those rocks lined up that way. But then as time went on and the ocean was moving apart, the poles reversed. And now there was what we call sort of a reverse magnetism. And now those rocks that are being formed and the minerals in them are lining up this way. The older rocks still maintain the kind of polarity that they had when they were formed, but the new ones now have sort of a different marker. And then in time, perhaps, that it switched again. And now we're back to sort of normal magnetism, that south is pointing south. And as you can see here, this way, these rocks that were formed there are there and there. And then these rocks that were formed spread apart are now there and there. And it creates this sort of double band. As they come up, it creates this double band. That sort of evidence said, you know what? I think the seafloor is spreading apart and the evidence is in the rocks. Excuse me. If you click here, you can watch a pretty neat video on that to see how that happens. Okay? All right. That's the end of our first set of notes. We'll come back talking about plate boundaries in the second set. See you then.